Hello, this is a course on quantum information for engineers. My name is John Jian. I hold degrees in both physics and engineering, and I have worked as a telecommunications and software engineer for 30 years. Therefore, I view quantum technology from an engineer's perspective, which turns out to be the easiest way to understand it. This perspective can be summarized as follows. First, a quantum bit, or qubit, is a quantum wave that can carry information. Second, an ideal qubit is free of noise and error, and can therefore represent a pair of complex numbers that support tremendous computing power. Third, this computing power is limited by what I call the readout bottleneck of qubits. Only when we have an algorithm that can overcome this bottleneck can we truly harness the power of quantum computing. The course will begin with the fundamental concepts and then provide a high-level overview of quantum technology in Chapter 2. Starting from Chapter 3, we will introduce the mathematical model of qubits and look more deeply into the readout bottleneck. In the later chapters, we will study several well-known quantum algorithms, including the famous Shor's algorithm, and classify these algorithms into design patterns. First, what is information? In our brains, information is invisible and seems to be abstract. But in everywhere else, information is symbols, useful symbols. In computers, and actually in all machines, information is represented by numbers, which are called by different names depending on the use cases and the level of the technology stack we care about. At the bottom of the stack, quantum technologies use qubits or quantum bits as the information carriers. The polarization and phase parameters represent or carry information. In a computer, information is represented by the voltages of some transistors. In a Wi-Fi channel, information is carried by amplitude and phase pairs of radio waves. Carrier is a term borrowed from communication engineering. Establishing relation or mapping with the upper-level code is called modulation in communication engineering. Code is the communication and information theory term on the information representing numbers when our software needs to adapt to the specific hardware. In computers, we may call them bit, byte, integer 16. These concepts are all familiar to communication engineers. However, the demodulation of a qubit or readout is not the inverse of modulation. We can only read out 0 and 1. This is what we would call the readout bottleneck of qubits. It is a form of quantization error in engineering terminology. So, what is a quantum bit or qubit? It is a quantum wave well controlled to be free from the disturbance of noise. Quantum physics says that the smallest of everything is a quantum wave. Electrons are quantum waves. Electrons trapped around positively charged nuclei are the most promising types of qubit technology. A photon is the smallest unit of light wave. Confining it in optical fibers also makes a good qubit. Because of using the smallest unit of wave, an ideal qubit is noiseless. That is the only advantage over other types of carriers. Therefore, its parameters can map to a pair of complex numbers to be the hardware code. For the same reason, a qubit can be measured only once. This is the cause of the readout bottleneck. Now moving up to the hardware code level, fundamentally a qubit's hardware code is a pair of complex numbers. There are two other simplified types of code. Because the codes are complex numbers, we increase precision and capacity tremendously. To find a factor of a large number n, the brute force method with a classical computer is to go through the numbers smaller than n/2 to find any of them can divide the big N. Because pairs of complex numbers can also represent many integers, rational numbers, and real numbers, a quantum computer can calculate whether n1 can be divided by any of the a to the power of x for each chosen a. Therefore, Shor's algorithm requires us going through or iterate over only a's to find whether n has a factor. The possible number of a's is the small n. Now, let's pause for two exercise questions.